Okay, welcome everyone to the Tutte Colloquia. We're very happy to have ShacharLovett, who is a professor in the Computer Science and Engineering Department at UC San Diego, and whose research spans a very broad range of topics in theoretical computer science, computational complexity, additive combinatorics, and beyond. And today, Shachar will tell us about point location and active learning half spaces almost optimally. Shachar.
Okay. Thank you, David. So yeah, thank you for coming. And really, if you have any questions, then please interject and don't wait till the end. I mean, this is supposed to be, somewhat informal. And I'm hoping that I can sort of get many of the ideas across. And this is all based on joint work with Max Hopkins and Gaurav Mahajan, who are students at UCSD, and Daniel Kane, who's a faculty. And this is some line of works I'll tell you about that we started a few years ago, and this is the latest version of that. But as you'll see at the end, there's still, I think, very natural open questions here, so I'm hoping some of you would be interested in. Okay, and this work, the title says point location and active learning. Well, point location is a problem coming from computational and discrete geometry, and active learning is a problem coming from machine learning, and sort of interestingly, these two problems, even though they're coming from different domains, mathematically they're the same problem, and it would actually be useful to use these sort of two viewpoints. So I would sort of, for the most part, stay with the machine learning viewpoint of that because it would be more convenient, but I would introduce both. So the starting point is this area in machine learning called active learning. So I'll tell you what this is. So it's sort of active learning starts from the following sort of observations that people have made probably closer than two decades ago, but even more true today, which is it's very easy to get a huge amount of unlabeled data. In particular, today there are hundreds of millions of new images in Instagram or tweets in Twitter or whatever other data set that you're interested in. However, they're not very useful because if you think about the learning algorithms people apply in the wild, for example, today deep learning is very popular. It usually needs labeled data. So the question is, how do we bridge this gap? Because labeling data is expensive. Assuming that, for example, you want to be able to say, well, here's an image of a cat or a dog or a flower or whatever, you can't have people sit and tag 100 million new images every day. It's not possible. So you need to do something smarter, not just to label all this data. So what can you do? Well, the idea of active learning, sorry, there was a question? I heard something. Okay, maybe not. Okay, so the idea behind active learning is that, well, you don't really want to do that. So you're saying my learning algorithm gets a large amount, a batch of unlabeled examples, and it has an oracle. And this oracle says, here's a label, here's an example. What's the label of this example? So imagine you're downloading like a huge amount of images from Google, hundreds of millions of images, and they're all unlabeled, but you have, access to people, and you can pay them maybe 10 cents to label a picture, and you have a budget of $1,000, so you can only label 10,000 images. Somehow you want to choose smartly which images you want to label, such that the data that you get is going to be useful for you in sort of understanding all these images. And this is in contrast to passive learning, which is sort of the most standard methodology where you just assume that your learning algorithms get just all labeled examples. And of course, the hope here is that if you smartly choose which examples you label, or in this model you query the label of, then somehow that's going to be useful for you. So I want to show you two examples, very simple examples. First, for a very simple scenario where this is useful, and then a very slightly less simple, but still simple scenario, but this is not useful. And then we can see, well, what do we learn from that? So here's the first example, and that's going to be a very, very simple example of just a one-dimensional problem where we will see that active learning is indeed useful. So there's something maybe to be gained from that. So here is the scenario. So you're given endpoints on the real line, and you know these points. So these are your unlabeled examples. And you know that they are labeled plus or minus. So for simplicity, I'll assume here throughout the talk, the labels are just binary labels, plus or minus. And what is a labeling? Well, there's some threshold that you don't know. That's a secret threshold. Everything to the right of this threshold is labeled with a +1. Everything to the left of this threshold is labeled with a -1. But you don't know this threshold, you don't know this labeling, So what you're really getting is these points. Now, and the question is, well, what can you do? What queries should you make so that you can learn all these labels without actually querying all these endpoints? Now, in this one-dimensional problem, there's actually a very simple solution, which is you do binary search, right? So you start by querying the middle point. Let's say you get a +1. So you automatically know everything to the right must be a +1 by the promise we have on how these labels are generated. And then you take the middle point of the remaining points. Let's say it's a -1. You know everything to the left must be a -1, and you keep going, right? So in that way, you only made log n queries, just asked the labels of log n points, but you were able to infer the labels of all endpoints for free, basically. So remember, here in this model, we just pay for the number of label queries we make. We don't really care how much time it takes us later on to infer the points. So here we really did well. We just made log n queries. We inferred all endpoints for free. And you think about this initially and say, well, that sounds great. Maybe we can extend this to 2 dimensions or higher dimensions. And unfortunately, even in 2 dimensions, there are scenarios where this is impossible. And this example I want to show you is from Sandra Dasgupta from close to 2 decades ago. And so what's the problem first? What is the problem of this sort of labeling in 2 dimensions? So it's a very similar problem to the previous one I told you, except now we move from 1 dimension to 2 dimensions. So now you have endpoints in 2 dimensions. So these are all these sort of black points here inside the square. By the way, do you see the cursor when I move it around?
Yes, we can see that.
Yeah, perfect. So you see all these black points. Now you know these black points, and they're labeled by this green line that you don't know. So the green line you don't know, it's a secret green line. You're probably that there is a green line such that on one side all the points are +1, and on the other side all the points are -1, and you need to figure out this labeling. So really what you get to see is these black points. And now the question is, can you still do binary search and recover the labels of all these points? Now, when you first think about this question, it seems that, well, sure, there's a way to do binary search. Maybe you first go with the x-axis, then the y-axis. Maybe there's some things you could do. But unfortunately, there are scenarios, you can build examples where there's actually nothing you can do. So you cannot do binary search in 2 dimensions in this way. And so in the worst case, you will need a linear number of queries already in 2 dimensions. So what is this example? Here's an example. Let's say you take your endpoints and you just put them on a circle, or more generally, you put them in some convex position. And let's say I even give you this promise that the line that I'm giving to you has the following special guarantee. It separates exactly 1 point from the rest. So 1 point gets a +1, all the rest get a -1. And now you want to figure out which point is this +1. Well, you're going to start querying points, but you're going to see -1 until you find this 1 point that's a +1. So there's nothing you can learn from queries that are -1. So you need to essentially query all the points until you find the 1 point that's a +1. So in this example, you will need a linear number of queries, while in the 1-dimensional case, we only need a log n query. So somehow it seems that we lose a lot already going to 2 dimensions. And the question is, what can we do? How can we recover this nice behavior we had in 1 dimension when we move to 2 or more dimensions? So there are 2 types of solutions you could make. One solution, the first solution, is the one that's more common in the machine learning literature, is saying, well, maybe this previous example we had, this sort of point on the line, is sort of adversarial looking. Maybe let's assume that's a point, data coming from some nice distribution. Maybe it's a Gaussian or a mixture of Gaussians or something that looks nice. And so we avoid these adversarial examples. So that's one type of solution. There has been lots of work on what are nice examples in which you can do active learning efficiently, but I will not be discussing this at all. So what I will be talking about today is this alternative solution, which is what if I'm allowed to query other points beyond the point that I'm giving. So for example, in this circle example in 2 dimensions, what if I'm also allowed to query these red points outside the circle? So remember, the points I care about labeling are the blue points. But now I'm giving you an extra power. You can query any point anywhere in space, or in this case in the plane, and you want to recover the labeling of the point that you got. And it turns out in this example, by querying points outside the circle, you can actually recover binary search. So I mean, what I want to tell you is, well, how can we do such things in general? So first, let's try to define this problem a bit more formally. So this will be active learning in high dimensions. So here is a problem that I'll be talking about throughout the talk. So let's spend a minute or two making sure that you all understand this problem. And if there are any questions, please ask them now. So here's my assumptions. There is a known set of points, x, in d-dimensional Euclidean space in RD with endpoints. Now you know this point. This is not part of the input. This is just a known set of endpoints. What you don't know, there is a unknown hyperplane. And for simplicity, I'll assume it's homogeneous, because if it's not, you can always make it homogeneous by moving to one dimension up. So let's assume for simplicity it's homogeneous. Homogeneous here means that hyperplane goes through 0. And h is just going to be the normal of this hyperplane. So this hyperplane is defined by its normal vector h. And I'm going to label each point depending on which side of the hyperplane it lies upon. So because h is a normal, it's just going to be, you take the inner product of your point x with h, and you ask, is this inner product positive or negative? Am I on one side or another side of the hyperplane? And my goal will be to learn the labels of all points in x. So I want to learn n labels. And I have an oracle, and this oracle, I can give it any point I want in RD. Could be one of my n points, could be completely arbitrary point. And this oracle is going to return to me the label of this point. Now, in the machine learning literature, this is called membership queries. And even though some people might argue they're not practical, there's of the limitation of what you can hope to do. So we can justify why this makes sense for some theoretical studies, but for now, think of it as a completely combinatorial question. So the question is, you get n points in RD, they're labeled by unknown hyperplane, you want to learn these n labels. You can ask the label of any point in RD, how many queries are needed until you can learn the labels of these endpoints? Okay, that's a question. Is this question clear? So now is a good time to ask questions if there's something unclear about the statement of the question.
Shachar, I mean, because this is a query complexity question, you could hope to just completely characterize the answer unconditionally, right? I mean,
yes. The hope here is to say there is something you can say that is, it's just a query complexity question. It should not depend on this, maybe on the structure of the point, just on D and N.
Got it.
Okay. So actually, that's a very good point. It's a query complexity question. Of course, in reality, you would want to say, well, these queries are not something completely arbitrary. They should be simple in some ways, and then it works on that. And you want to say, well, this should be computationally efficient. But as you'll see soon, even the query complexity question is not known. So even here, there's a lot of gaps in our understanding. So that's going to be the main focus of what I'll talk about, the query complexity question. Any more questions about that? Okay, so I'll continue, and if you have any questions, just please stop me and ask. So let me start by a simple lower bound. Or actually, maybe before doing the lower bound, I'll show you, now I'm going to show you this dual question coming from computational geometry called point location that is mathematically equivalent to it, but actually has been studied much more because it has a lot of connections to algorithms in computational geometry and discrete geometry. So what is this dual problem? So it's going to look very similar, but sort of in a dual way. So in this dual problem, we are given a known set of hyperplanes H that partition, again, RD into cells. And I'm going to show you an example soon. So you know them, you know the partition. There is an unknown point X in RD that you don't know. And your goal is to find the cell in this partition where X belongs to. And again, there's an oracle that can answer queries. And the queries here are the following form. You can give it an arbitrary hyperplane, and it will tell you on which side of this hyperplane X lies, on the left or on the right. And again, the question is going to be, how many queries are needed? So let me just show an example here. So maybe here, imagine the blue lines is, again, in 2 dimensions, the blue lines partition the plane into regions, cells. So some are, like this triangle here, or maybe this polyhedra here. So some are open, some are compact, some are not, doesn't really matter. Just partitioned into cells. And then there's this input I don't know, this red star here. And the questions I can ask are of the following form. So what I want to learn at the very end is that it lies in this cell, which really means it's below this line, and it's below this line, it's above this line, it's on the right side of this line, and so on. This is what it means to be in the cell. What access do I have to the input? Well, I have an access by an oracle, and I can give the oracle a line, like in this case, this red line. It will tell me, well, this point is on the top, on that part of the space. Or it's actually maybe this line, which is not one of the lines I got, and it will tell me the red point is on this side of the plane. Right? This is the queries I could make. And I'm claiming that this question is actually the same question as this active learning question, just a dual version of it. So why? So again, what is this active learning question? Let's try to formalize it a bit more. So we're given a set, an unknown set of points x in RD. There is an unknown hyperplane. My goal is to learn the label of the points I got. So my goal is to learn what is the label. It's the sign of the inner product of x and h, which will tell me if it's positive, then x is on one side of the hyperplane. If it's negative, it's on the other side. So I want to learn this for these points x I got, but I could ask these questions on any point in space. So I can ask about any point I want. What is this point location question? It's exactly the same mathematical question where I just replace thinking about points as hyperplanes and hyperplanes as points. I just dualize points and hyperplanes. So now we have a known set of hyperplanes in RD. We have an unknown point in RD. And I want to find exactly the same. Why? What is the cell of x? The cell of x is just determined by knowing for each hyperplane is x on the right or the left, meaning the inner product of x and h, positive or negative, for all these hyperplanes. And what can I do? I can query arbitrary hyperplanes, which is again the same thing. It's exactly the same mathematical question, except that where I replace the role of, am I thinking of x as points or as hyperplanes, and similarly for h. So it doesn't matter which question you study, you're going to solve the same problem. But there is a difference, because when you think about the active learning question, you naturally are led to think about techniques coming from the machine learning community. While when you think about point location problems, you naturally tend to think about techniques coming from the computational or discrete geometry community. And these techniques are different. So now you can hope to maybe combine these two sets of techniques and get the best of both worlds. And we're going to do this to some extent. So now let's start talking about bounds. So what's a lower bound? So remember, this is a query complexity question. And I claim that in general, there is a very simple lower bound you can get. And the main question is, can we match it? So again, what's the setup? We have endpoints in RD. We want to label all these endpoints using a few queries. And then claim you need at least something like a d log n queries. Why? Well, here's the proof. First, let's ask, at the very end, how many possible answers could I get? Well, an answer should be labeling all these endpoints, but not all 2 to the n labelings are possible because the labeling have a structure. They're coming from a hyperplane in d-dimensional space, partition this set of points into negatives and positives. And if you ask yourself, well, in how many ways can I partition endpoints, n generic points in RD using a hyperplane, the answer is n to the d. So I need to distinguish between n to the d possible answers, and each query the binary query. When I give my oracle a point, it gives me plus or minus, so I have 2 answers. So if I need to distinguish between n to the d possible answers, and I'm using queries with binary answers, it doesn't matter what is the structure of these queries, I will need d log n queries, log of the number of answers. So that's the best I could hope for using any type of binary queries. Another question is, well, my query is actually limited. They're coming from these geometric queries. So can we match this bound? Can just using geometric queries, can we match the lower bound that holds for any binary query, or either additional information or bottlenecks coming because we are limited to using geometric queries? So that's the main question that we'll try to study. And in fact, we're not the first one to study. This question has been studied for the last probably 50 years, 40 or 50 years. So here's what we know in terms of upper bounds. So this question was actually the first result here is by Hufdermeyer in the early 80s. And he studied the special case of this problem, not this generic case, and he got a lower bound that was very surprising at the time. It was poly n and not exponential in n number of queries. And then there was Meiser was able to generalize these techniques of Hofdermeyer and show that in general, if you have n points in RD, you need some poly d log n, and he could get d to the 5 log n, which already is very surprising. It shows that if the dimension is small and n is big, you need log n queries instead of n queries. So we can get back this binary search behavior, but we pay something. The dimension is not d, but some poly d.
Sorry.
Yes.
Can I ask, why does this avoid the problem that you showed us on the circle, the example on the circle?
Because you're allowed to ask the labels of points that are not one of these endpoints that you got, but you can allow to ask about other points.
Oh, got it, thanks.
Or in this dual version of space partitioning, you're allowed to ask about other lines or hyperplanes, not just the one that you got. This turns out to be crucial.
Thanks.
So there have been a sequence of works, and the last one was by me, Daniel Kane, Shai Moran, and Jiepeng Zhang about 3 years ago. And we showed that if the points are nice in some way that I don't want to define here, then actually using simple queries that, again, I don't want to define here, you can get very close to the d log n lower bound. So the main thing that sort of remained open after our work is, what can you say about adversarials of points? So don't assume the points are nice in some way. Assume the points are completely adversarial. So again, this sort of takes, this is very different than the type of assumptions people make in machine learning. This is more in line with the assumptions people make in discrete geometry, where you want to understand adversarial examples, or any example, any input. And can we still match this d log n? And the best that was known, and again, all of these works, the first 4 works here, all of them come from people working in computational geometry community using sort of space partitioning techniques that were originated in computational geometry and discrete geometry, and also are used in a lot of computational geometry algorithms. And it seemed that the limit of these techniques was d squared, roughly, up to log d factors. And what I want to tell you about is this new work that we had, where we can get this to be much better. So the new result we have has 2 parts, the bound. The first part is what we were hoping to get, which is something like very close to d log n up to some poly log d factors. But then we also have this other term in red here that is not very optimal, which is, again, it's nearly an NRND, but this little O of 1 term is actually hiding some annoying factors. I'll tell you about at the end, more than poly log d factors. But I believe, and I'll tell you more about this towards the end, that this part could probably be improved. So my goal in this talk is to tell you what ideas come into this bound, and some of them are going to be about techniques that work for any type of input. But the new ingredients is about trying to understand structure inside the input and utilize structure to fine-tune algorithms to work better, which is a new ingredient in this work. Also, I want to point out that, yes, sorry.
Do these bounds also work for the dual problem that you had earlier?
Yeah, it's the same mathematical problem. They're exactly the same. There's no difference. Another thing is that our algorithm here is randomized. Now, actually, all of these previous works are all randomized by nature. Some of them can be de-randomized, some of them cannot be de-randomized, but all of them are randomized, where the de-randomization is usually by some compactness type argument. It's not like an effective de-randomization. So in many of these, even for like the worst bounds, there are open questions about de-randomization. But also our work, as you'll see, naturally is going to be a randomized algorithm, because the natural approach here actually stems from this computational geometry approach, builds on random samples in a very natural way. So I'll tell you about that. So that's the main result I want to tell you about. How can we sort of shave this d squared to something very close to linearity? Any questions so far about the results?
Are you assuming that the points are in general position?
No, they're completely arbitrary points. No assumptions whatsoever. You could assume they're in general position. It shouldn't make a difference, but we don't have to. Actually, if they're in general position, some parts become slightly simpler, but nothing major changes. More questions? Okay. So now let me tell you about the techniques that go into this proof. So I'm going to do it in steps. But again, just to recall the question, so we have n point in RD, arbitrary points, no assumptions. We have an unknown hyperplane. My goal is to learn the labels of all points in X using close to D log n queries, which is at the lower bound. And I can query the label of any point in RD. And again, the hope here is to, by choosing these queries, in an appropriate way, to minimize the number of queries as close as possible to this information theoretic lower bound. So I'm going to make two definitions here that are going to be convenient for us later on. First of all, I want to make an assumption just to simplify some normalization aspects. I could assume that the points and the hyperplanes are unit vectors because all that I care about is the signs of inner products. So changing the norm doesn't change anything. So I could assume to begin with, just rescale the points to be unit vectors, doesn't change anything. Since I don't know H anyways, I can assume it's a unit vector, just rescale it in my head, doesn't make any difference. Now, two definitions. One is a label. So the label of X and H is just what I'm trying to learn. It's a sign of the inner product of X and H, whether X lies on one side or another side of the hyperplane. Margin will be another parameter that's going to be very natural here, will be the absolute value of this inner product. So now I'm ignoring the sign and just is it big or small. Okay? So just make sure that you remember both of these definitions because I'm going to reuse them again throughout the remainder part of the talk. So labels are the sign of the inner product. That's whether you're positive or negative. Labels have binary values. Margin is how large is this inner product. And as we will see, large margins is easier, small margin is harder. Okay. And what's going to be a general paradigm? The general paradigm, we're going to employ the following thing. We would like to make something like D, close to the queries. And we want to infer the labels of half the points. Okay, by making something like the queries in a judicial way, we would like to then say we can, without making any more queries, infer the labels of half the points that we want to infer the labels of. Then we're going to remove these points and repeat this process. And because we're assuming nothing about the points, we just repeat this process. Overall, this would require D log n queries. So the main question is how can we get this to work? But that's going to be the general approach. And again, when I'm using this sort of tilde sign, I'm going to ignore something like polylog D factors throughout the talk here. I mean, you can try to optimize them, but I will not care about it here. So just whenever I tell approximately, I'm ignoring polylog D factors. So I only care about factors polynomial in D. And in fact, as you'll see, we won't really have to care about n. N could be very big because in this main iteration, we're just going to infer half the points. So n will not come as a parameter in our analysis. We'd like to make something as close to D as possible queries, and then learn the labels of half the points. Okay, is this clear? Question so far? So the goal is to implement this general paradigm. Okay. So I'm going to build the algorithm in steps. So every time try to generalize it a bit more. So the first step that you want to understand is what if my points are not somehow adversarial looking, but sort of random looking? And this is just for intuition. I mean, really what we try to understand is what if many of these points have large margins, so they're far away from the hyperplane. Which is in this case, actually very simple things you can do to learn the labels. But that's going to be a good starting point. So assuming that my points here are random, and again, random unit vectors, and the insight is going to be that well, they should typically have large margin. Why? Well, let's remember what a margin is. So H is a normal to this hyperplane, just some unit vector, some fixed unit vector. Let's say I choose a random unit vector X. And I'm asking you, what should be the margin of X and H? Remember, what is margin? It's just the absolute value of the inner product. And just from very simple calculation, it's something like 1 over root D. Again, the actual value is 1 over root D, doesn't really matter. It's big. It's not really, really close to 0. And again, this is just for intuition. We don't really have random points. But what we could say is that, well, if this was really the case, then with high probability, let's say half the points should have large margin. And we would like to learn these points with something like D queries. And more generally, we would like to say, well, if I have many points, now we can forget about random points. If I have many points where the margin is not tiny, 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 I would want to learn their labels using a small number of queries close to D. And this you can do very, very easily. So why can we? So I want to show you in some detail, just so that it's a good starting point, it's a good warm-up, why if many points have large margin, it's actually very easy to learn their labels using something close to D queries. So here's going to be my assumption. Now forget about random points. Let's assume half the points have margin epsilon, some epsilon that I know. I want to show you how using a very simple algorithm, you can learn all of the labels using something very close to D queries. And actually, if you do the math, it's something like D log D over epsilon queries. And again, our epsilon is to be 1 over root D, so it's really D log D queries, very close to D. What's the idea? Why is large margin easy? So here's the idea. It's a very simple idea. Let me denote by H the hyperplane by H1 up to HD. So this is the D coordinates in the standard, basis of this hyperplane. And let X be some point. Also write X as X1 up to XD. So what is the inner product? Just the sum of HI XI. Assume I could estimate each HI up to small enough error, epsilon over D. And I'll show you in the next slide how we can do it using binary search in a very simple way. So I'm claiming this is enough. Why? Because then I can estimate the inner product of X and H up to error plus minus epsilon. So if I know that this inner product is big in absolute value, it's more than epsilon, then approximating up to small enough error is enough to know the sign. Right? So if a point X has margin more than epsilon, which to remind just means that the absolute value of this inner product is more than epsilon, then approximating HI would be the good enough thing to do. So again, the whole point of this is to say, if I have many points of large margin, then my life is easy. Life is good. But of course, if this inner product is really, really close to 0, then this is useless, right? Then approximating each HI will not tell me anything about what the sign is. So this is only useful if the margin is big enough. So let me just show you just one slide how we can estimate each HI up to small error. Again, that will be very, very simple technically, but I just want to make sure that you all feel comfortable with the notations I have here. So my goal here is to estimate each coordinate up to some small enough error. What is the coordinate? HI is just the inner product of H and the basis vector EI. So first of all, I can compute the sign of all D of them using D queries. And again, these are just the labels. So here I'm just making sure that you all understand the notations. What is the label of H and EI? It's just the sign of the inner product of H and EI, just the sign of HI. So I can do that using D queries. Now let's find the maximum one. So let's say I star if the HI where the absolute value of HI is maximal. Again, you can do that using D queries. Well, now you need to query points of the form EI minus EJ to do that. So you find the maximum one. And then really what you estimate is the ratio of HI over HI star up to some small enough error, epsilon over D. Now this is a number between 0 and 1, or between, say, -1 and 1. So I can do it using binary search, using log the error that I want to do. And if you really think what type of queries I'm making, they look like that. So you see, all the points I'm making here, this EI star minus alpha EI, 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 these are not the points I got, right? I got some endpoints, but I'm allowed to use arbitrary queries, which I'm using it here. So using these arbitrary queries, we can very easily approximate the hyperplane into very high accuracy, which is good enough to learn the labels of all the points that are far enough for the hyperplane. So really, here is a picture you should have in your mind. So here is a hyperplane, and using sort of very simple strategy, we can get a good enough approximation for it. So I can learn the labels of all these points on the blue side. But what I don't know is what are all the labels of all the points that are close together. Actually, the algorithm I just told you will not quite work because it's not clear how I would actually know that the point is far or close from the hyperplane without actually making a query, right? So if I knew a point was far from the hyperplane, this would tell me is it positive or negative. But to know if a point is far from the hyperplane, I would actually need to do some more queries. But actually, there are easy ways around it. Let's ignore this. It's a small technical point. Let's ignore that for now. But my point is that it's easy to deal with all these points far from the hyperplane using this simple approximation. What is not clear is how do we deal with points close to the hyperplane, where the margin is very small. And again, since these points are assumed to be arbitrary, adversarial, all of them could be exponentially small, adversarially close to the hyperplane. Maybe initially all the endpoints are very close to the hyperplane. So this technique learns no points. So the question is, what can we do then? But at least we know how to learn points that are far. Sorry. So that's the first step. So we learn the points far from the hyperplanes. What we have left are points close to the hyperplanes. So this technique doesn't solve at all. Any questions so far about this first step? Okay, no. But this was easy. So now what do we do? How do we deal with points close to the hyperplane? So here's going to come the second ingredient called vector scaling. That's going to allow us to assume that at least some points can be moved to be far from the hyperplane by some appropriate scaling. So what is vector scaling? So the idea is to do the following thing. So assume even there are no points of large margin. Maybe all the points are extremely close to the hyperplane. And the idea that we can do basically a non-linear transformation, which is actually linear transformation plus rescaling, that's going to maintain the labels, but is going to change the margin in some unpredicted way. So there is hope that if we make it in a smart way, maybe we can at least push some of these points to be far from the hyperplane, and then we can apply the previous technique. So what is this vector scaling technique? So, okay, let me do this in steps. So let A be some, invertible D by D matrix with some linear transformation on RD. I'm going to make the following definition. A acting on a vector X is the following thing. So I apply A on X, and then I rescale so that the answer is a unit vector. So notice this action is not linear. So A times X, when I write AX, I just mean the standard matrix vector multiplication. When I write A acting on X, I mean rescale to be unit vector. So now it's no longer a linear transformation. And let me also denote by A star the adjoint operator, so that just a standard adjoint operator, so that inner product of AX A star H is just inner product XH. So imagine doing the following transformation. X is my set of points that I know. H is this hyperplane that I don't know, but it exists. Imagine in my mind, I replace X with AX. What is AX? I just apply A as an operator on every point. So I multiply every point in X by A, and then I renormalize to be a unit vector. And I do the same on H, but not using A, using A star. Now I claim that doing that is going to keep the labels the same, but it's going to basically randomize or at least change the margins. So at least there is hope that even if initially all the margins were small, after applying such transformation, margins could become big. So let's see why. So that's a claim. And let's do the calculation. What is the inner product of A applied to a point X with A star applied to a vector H? Well, just apply the definition. So A acting on X is A multiplied by X divided by the norm of it. What is A star acting on H? Well, it's the same thing, A star multiplied by H divided by the norm of it. Since A star and A are adjoint, this inner product just simplifies to X inner product H. So what do we get? We get that these two values, the sign is the same because we divide by something positive, right? Norm is always positive. So the labels are the same, the signs are the same. However, the values can arbitrarily change, right? These norms could be tiny, could be big. There's no guarantee that the value, which is a margin, stays the same, but the signs stay the same, the label stays the same. So the idea is that, well, maybe you can apply A in some judicial way, such that now many margins become big. So can we guarantee that? So again, here I just wrote again the definition. So this is A acting on X. Definition is multiplied by A and renormalized to be a unit vector. A star is a joint operator, satisfying this property. We replace X and H by applying A on X, or any point in X, and applying A star on H. So I want to claim that I can actually do that, even though I'm only going to do it in my mind. I could assume that I can apply N my points. Why? First, as we said, labels stay the same. Remember, I don't know H, I don't know A star of H, but the labels stay the same. So I can do it in my mind. Also, I can claim, I'm claiming I can simulate queries, because if I want, for whatever purpose, to simulate a label query on a point X with respect to the new H, A star H, then first of all, the absolute value of that doesn't really matter. So this is the same as A star H. And you can do a very simple calculation, see that this is actually the same as this label, A minus 1XH, which I can just use in my algorithm. So if I want to simulate queries of a point X with respect to the hyperplane A star acting on H, I can instead compute the label of A minus 1X on my original oracle, so I can simulate queries. And lastly, as we saw, the margins change. So at least there's hope we can get them to be big. So this is why we can actually do it. This doesn't explain why this can actually be useful. So the next slide, I'm going to explain why this might be useful. And for that, we need the following theorem. So one more bullet. So first of all, let's actually look at the second bullet first. So a set of points y in RD is said to be in isotropic position if basically its covariance matrix is the same in identity, scale of identity. Equivalently, if for any unit vector v in RD, if I compute the sum of the inner product of points of y in this direction v, it's just the projection in direction v squared, and I average that of all points of y, I always get 1 over d. So again, this basically says that the covariance matrix associated with y is 1 over d times the identity, scale of the identity. And the way you want to think about this is this set of points in any doesn't look, it's not very skewed. It looks like a ball in some way, in the sense, at least in the L2 sense. I mean, there's no one direction where projections are too big. It doesn't look like a very lopsided ellipsoid. Now, what's the theorem? The theorem that we have here is the following thing. If a set of points x in RD is not degenerate, and I'll tell you what degenerate is in a second, then there is always a linear transformation A such that A acting on X is in something I'll call approximate isotropic position. So approximate basically means its equality is roughly 1 over d. And again, I'm not going to give you exactly the right definitions here, but and what is not degenerate, also I won't define it, but I'll say non-degenerate. If it is degenerate, then you cannot do it. So it's an exact characterization. And if it's degenerate, it's so degenerate, there are very simple things you can do to basically reduce dimension. Like one case where the points are degenerate is like they all lie in like a low-dimensional space. Like they all lie in like a d minus 1 dimensional space. Or maybe half of them are in d over 2 dimensional space and the other half in some orthogonal d over 2. So really, really degenerate cases. So what we can prove is that either the points are so degenerate, you can actually decompose them in very simple ways and solve each problem independently, or if they're not degenerate, then you can always find A such that A of X is in essentially isotropic position. And there have been actually several works in the literature doing that. So actually, Forster, which is the first one in the CS community, his definition of non-degenerate was general position. And actually, these works of Barthe and Karl and Lieb and Loss, Dvir gave much more general definition. We can be not in general position, but just not very degenerate. And actually, what we have is a complete characterization of this. So we completely understand this problem now. And this is actually also implicit in this work, in this Karl and Lieb and Loss work. But anyway, we have now a complete understanding of that. So unless my points are completely degenerate and I can solve this problem easier, I can always find A, or at least in this L2 sense, they look nice. Now, what does this mean on the margin? Let's say I choose V now to be A star of H. Remember, I don't know A star of H, but it's some unit vector. And we get this guarantee for any unit vector. So it's in particular true for this specific unit vector. So it tells you at least n over d points should have large margin. It cannot be that almost all the points have essentially zero margin, because we know that the average margin square is 1 over d. So at least 1 over d fraction of the points should have large margin. That's the Markov. So at least some fraction of the points has large margin. So that's a benefit of vector scaling. We can move from an initial situation where it could be that no point has large margin into an equivalent scenario where now at least some fraction of the points have large margin. So what can we do with that? Well, we are back in business. So let's see, where do we stand now? So we apply vector scaling initially. We can guarantee that some 1 over d fraction of the points have large margin. Now we can use these techniques we had from large margin points to learn the labels of these n over d points using something like d queries. But since with d queries, we only learn 1 over d fraction of the points and not half the points, this will not give us d log n, this will give us d squared log n queries, which is now worse than what we were hoping to get. So actually, this is a way of reproving this d squared log n bound of Ezra and Sharir using, I think, what is a simpler technique. But this doesn't tell us how to get beyond d squared log n. And in fact, this d square is a barrier because for many of these previous techniques, including these vector scaling techniques, this is a limit. So you can actually build examples that show that you cannot improve vector scaling. So if you just are going to apply techniques that apply to arbitrary set of points without actually trying to understand the internal structure of this set of points, you're bound to get stuck at d squared. You cannot go below d squared. So here is the point where we actually had to find new techniques, completely different techniques to go beyond d squared. So here's again a good point to stop and see if people have any questions.
Why again is it that vector scaling can't be improved, that this is optimal?
So here's one example. Imagine you take sort of d unit vectors, and inside and near each unit vector, you take d points, which are very, very, very close to it. So these points are in isotropic position. They have d squared points in isotropic positions. And assume now my hyperplane is really close to d minus 1 of them. So one set of d points has large margin, but the other d minus 1 sets have essentially margin 0. And you can show that even if you rotate this point, there's no way you can change this. But in this case, these points are very structured. They have basically, you can partition this squared point into d points. Each one is essentially a one-dimensional point. But you will not know that unless you actually look on the internal structure of your set of points.
I see. Thanks.
So really what we did is motivated by this example. We're asking, how can we, by given a set of points, find if there's a set of points inside that essentially lives in a low-dimensional space, at least with respect to this hyperplane that I care about. Okay, good question. More questions? Okay, so I'll continue. So now is the main new ingredient of this work, which is trying to understand the internal structure of the point set that we got. Remember, we know the point set, so we can understand the structure without making any queries. But the question is, what structure is relevant to this problem we're trying to solve? So assume that we are already in this isotropic position, and let x1 up to xn be my set of points. And again, assume, again, for the analysis in our mind, that I sort these points based on the margin. Now remember, I don't know the margin. To find the margin for its n points, I need to make at least n queries, so I don't know the margin. But again, in our mind, for the analysis, assume I sort these points based on the margin. Now let's look on these points. What do we know so far? We know from the isotropic position assumption that at least the first n over d points are going to have large margin. But again, we know nothing about the rest. And actually, you can build examples where all of them are going to have large margin, or you can build examples where the first n over d are going to have large margin and the rest are going to have margin essentially 0. So both scenarios are possible. So now what we want to understand is what is actually the structure of the margins of these points. So I want to argue that there are two scenarios possible. So let's plot the margins of this point in this specific order. So one scenario is that all the margins are relatively large. Maybe no point is too close to the hyperplane. All the margins are big. That's a good scenario for us. We know how to handle that. What's the other scenario? The other scenario is a sharp drop. They're large up to some point, and then they sharply drop into a very low margin. And what we'd like to argue is that, in some sense, one of these two cases must hold. And that in this case, the second case with a sharp drop, we can actually do a dimension reduction type argument and move to a low dimensional problem. So let's dig into that. So here's the lemma, and it says the following thing. So again, I'll quantify it a bit more in a second, but I'm saying take any set of endpoints sorted by margin. There is some number m between n over d and n, such that the following thing holds. The first m points are going to have large margin. But going from point 2m up to n, so the gap between m and 2m I don't care about, but from point 2m up to n, all the points have much, much, much smaller margin. There's a big gap between m and 2m. So in particular, if m is something like n over 2, then point 2 is mute, right? Just all the points have large margin, if m is n or something. But if m is much less than n, then basically we think that the sharp drop in this interval between m and 2m. And notice here that it turned out that the relevant scaling here is a logarithmic scale. So notice that what we care about sharp drops between m and 2m, which is the gap here is multiplicative, it's not additive. So it turned out that this looking at this logarithmic scale is the relevant scale to look at this problem. So now let me prove to you this lemma, because the proof is actually simple. So let me first slightly quantify it a bit more. So let's take some capital D to be large enough for whatever needs we need later. Like imagine D to the 100. You know, small d is a dimension, capital D is maybe D to the 100, something big enough. I'm claiming that there is some m between n over d and n, such that the first m points have margin m, capital M. The points from points m up to 2m, I don't care. But from 2m up to n have smaller, much less than m. So the gap of capital D between them. And also m that you need, the large margin of this first small m points is not too tiny. If capital D is poly D, it's sort of something like quasi-polynomial in D. Something like exponential in log D squared. So it's still pretty big. And actually the proof here is relatively simple. So we're just going to examine all the possible m's in a logarithmic scale. Or more specifically, let's make the following definition. Let ai, just for convenience, be the number 2 to the power I over d times n. So it's like n over d, 2n over d, 4n over d, 8n over d. So I have log d numbers starting from n over d, and every time I multiply by 2. And yi is going to be the point x corresponding to this index. So it's going to be point x in indices n over d, 2n over d, 4n over d, and so on. So we're looking at log d points. And because they are as a topic position, I know that y1 at least, which is the n over d point, must have large margin. And again, this 1 over d value doesn't really matter. Large. So the first point is large margin. And now I'm going to ask either a jump, or let's define a jump at index I if the margin of yi is much, much bigger by a factor of capital D compared to the margin of the next point in this sequence. So we're in this sequence y and y2 up to y log d in this geometric sequence. And we're asking either there's a jump at index I if between yi and y plus 1, the margin drops by a lot. Remember, because we're assuming the points are sorted by margin, the margins always decrease. But we're asking do they decrease a lot when I go from yi to y plus 1. Now, case 1, there is no jump. Well, in this case, even the last point has large margin. And since I only have log d points It means that the margin can only drop by a factor of capital D to the minus log D. That's the first case. That's where all the points have large margin. The second case, there's a jump at I. Well, in that case, take M to be AI, and then 2M is AI plus 1, by the way we define this. Right? So that's it. That's the whole proof. So the whole idea here that you want to examine these points, the margin in a logarithmic scale. So now what can we do with that? It's not clear how this is useful. So again, let's ignore now the exact quantitative bounds. So the first M points have some large margin. From points 2M up to N, all of them have much smaller margin. And let me write M as Kn over D, where K is some number between 1 and D. K is even a power of 2, but it doesn't really matter. So turns out you can use this to learn something very, very useful. So here's the lemma. It says, the above lemma plus the fact that these points are in isotropic position guarantees the following very strong structural promise about my points. There exists a subspace in RD of low dimension, something linear in K, with the following guarantee. Out of these M points with large margin, many of them actually have large projection on V. And also, all of the points in the orthogonal complement of V must have very small margin. So now we can actually learn about a space of dimension like D minus K, that all of these points have tiny, tiny, tiny margin. And how do we prove that? Is basically because V perp is all these points effectively spanned by these points 2M up to N. What do I mean by effectively spanned? I mean the point that's spanned with coefficients not too big. So you can show that these points also must have small margin. And you can show that actually a whole subspace you can span in this way. So why is this useful? So there's a subspace of dimension, something like K, where K over D fraction of the points have large projection on it. And also everything orthogonal to it has tiny, tiny, tiny margin. So basically I take all of my points and just project them on V. And if they still have large margin, I know that the margin must be roughly the same. So if we knew V, we could just take all of my points, project them to V, and now apply everything that we know, not in dimension D, but in dimension K. Because now we have a K-dimensional problem for which many points have large margin, but now many is K over D. So you see this parameter K depends on the internal structure of my point set. It could be big, it could be small, we have no control over it. But whatever it is, we can project to dimension K. So now we only need to query something like K points instead of D points, and we learn the labels of K over D fraction of points. So the number of queries we make suddenly becomes linear in the fraction of points we infer the labels of, instead of always being D. So like one problem we had before was, what if K is 1? What if we can only learn the labels of 1 over D fraction of the points, like in the example I told you about? Well, in this case, actually what we prove with 1 over D fraction of the points essentially lives in a one-dimensional space. So we can actually use a one-dimensional problem, not a D-dimensional problem to solve it. So putting all together, if we somehow knew K and V that we don't know, we'll have to figure out how to find them later. But assuming we knew K and V that depend on the internal structure of my points, but also on the margins that we don't know, then we can query basically K points. We learn the labels of NK over D, so K over D fraction of the points. And we just keep doing that until we make D queries, at which point we labeled half the points, and we can just apply our standard paradigm. So this will give us this D log N bound that we're hoping to get. And now the last order of business is, how do we find K and V efficiently? And then the main problem here is that they do not just depend on the point set, because that will be something we just do, before even doing any queries. They also depend on the margins. They depend on the hyperplane that we can't know, because this will require queries. So that's the last order of business. So before talking about that briefly, any questions so far? So this was one of the new main ingredients, understanding the internal structure of points and showing that whenever your isotropic set of points have many points with very small margin, it must be because your point set with respect to this hyperplane has many points that are effectively in no dimensional space. Okay. So the final step that I'll talk very little about is how do we find structure. So far what I showed you, and I actually gave you the proof, is we can guarantee the existence of this structure. And our algorithm relies on knowing this structure in the point set with the margins to basically do the labeling, but somehow we need to find this structure. Unfortunately, this is quite involved. To do that, the best way we know to do it is to use randomness to sort of try and detect it. This randomness turns out can introduce errors, but we don't throw the errors. So then we can use machine learning techniques, in particular some versions of boosting, to correct these errors. But then we still have this reduces some verification problem to solve it using recursion. And this is why at the end what we get is it turns out to be a very technical and involved algorithm. So the high level ideas are simple, but actually getting them to work and discovering this structure, the best way we know to do it so far, are sort of quite technical. But I'm hoping at least you got the high level idea behind the algorithm. So just to summarize, so the question I was talking about is this active learning of half spaces, and it has this completely equivalent viewpoint from computational geometry of point location problem. We have a known set of endpoints in RD and an unknown hyperplane. That's the active learning viewpoint. The dual one is you have n hyperplanes and unknown point. You want to learn the labels of all these points. You can query any point in space that you want. You want to minimize the number of queries. The lower bound is d log n for any binary query. The new upper bound we get has two terms. The first term that depends on n is very close to the lower bound. The second term is not so much. Now, what is this d to the 1 plus 0 of 1? I'll just tell you what it is. It turns out to be d times 2 to the root log d. Anyways, I believe this second term, there should be ways of improving it. That's the best we could do so far. And really, I mean, the first part is really about, we can get the first part without the red part if you're okay with a small amount of error. And the red part counts if you want to really guarantee no error whatsoever in our algorithm. So if you're okay with a tiny bit of error, you can actually get very, very close to the lower bound. And really in the machine learning literature, a little bit of error is what's called the PAC model, the probability approximate correct model, and the verified one is what's called the RPU model, which doesn't allow any error whatsoever. Anyway, that's a connection to machine learning. Let me tell you about a few open problems here. So the obvious one is just to close this gap. But another one I think is more interesting, if you want to take any of these things and make them applied either in machine learning or for computational geometry algorithms, is can we use not arbitrary queries in space, but some simple queries? And unfortunately, now we cannot do that because these vector scaling techniques makes very simple queries become very, very complicated because of this arbitrary change of bases and rescaling. And which gives us basically no control over the structure of the queries. On the other hand, we had previous work showing that if the points are simple, then a related but different techniques can work with very simple queries. So I'm hoping there's some way to get these two things to work together. Let me even say that even in three-dimensional space, all these previous works don't work. So even getting this to work in three-dimensional space with some sort of notion of simple queries or simple analysis is open. So the only way to do in three-dimensional is with sort of these complicated techniques. And also, like I told you, I think the current algorithm is really quite involved, and I really suspect is because we're just trying to minimize query complexity, and we don't really care here about computational efficiency or about even which points we query. There should be a much simpler, maybe more geometrically inspired or combinatorial inspired algorithm that just somehow simulates binary search. But again, we haven't found. This is, again, this problem has been open for the last 40 or 50 years. I mean, people have thought about this quite a bit, but I think most of the work has been done from the computational geometric viewpoint using space partition type ideas. And I feel like introducing machine learning techniques into the mix really helped us a lot here. So I'm hoping at the very end, there will be a much, much simpler algorithm to this problem. Okay, that's it. Thank you.
Thank you, Shachar, for a very clear talk. So at this point, I think maybe we should pause for maybe one or two questions. So if somebody has a question, please go ahead.
Hi, Shachar.
Hi.
Thanks for the nice talk. I had a somewhat open-ended question. So, I mean, you were describing things where you want to learn the labels of all points. I'm wondering, suppose I cared for less information, like suppose I was only interested in learning some statistics, like, I don't know, the simplest thing is just maybe the number of points that are +1 or the discrepancy, say the difference between how many are +1 and how many are -1. Is there hope that something better can be done?
That's a very good question. So about these specific questions, I don't know, and I haven't thought about them. Another question is, what if I only care about the labels of, let's say, 99% of the points, or
Right.
1 minus epsilon? So here are actually very simple techniques coming from already like the VC dimension type literature that said, if I only care about labeling with epsilon error, I could just sample one of the epsilon points basically and just their label. So you can always reduce to learning the labels of all the points, taking the appropriate sample. Yeah, if you want other statistics like the number of points, I'm not sure that's a very. These techniques, I don't think they would give you a better algorithm, even if you care about the simple statistic of the points.
Okay, thanks.
I think this is true of all the previous algorithms as well.
Is there another question for Shachar?
Does your structure theorem have applications anywhere else?
That's a very good question. I mean, I hope so. I mean, we haven't tried to explore, but there's nothing it's special for machine learning. It just says something about the stuff points in RD, and has the reposition, and its margin with respect to a vector. I'm hoping, yeah, maybe we can find some applications. It would be nice.
Maybe on a related note, can it be applied in other vector spaces?
What do you mean?
Well, like, for example, like, finite dimensional vector spaces.
Oh, but there, what do you mean by margin? Value, big, being small.
Yeah, okay.
I mean, everything here I think should apply to the complex field as is. I mean, we didn't care about it, but it should be the same. There's no difference. But I'm not sure for other fields what would make sense.
Thanks. Okay. Well, maybe at this point we should thank Shachar again, and we can move to the virtual grad house portion of our event.
Sharing.
Okay, so I stopped recording, so everyone. Oh no, I haven't stopped.